The purpose of today's activity is to verify the thin lens equation. And you know the thin lens equation says 1 over f equal to 1 over dO plus 1 over di. We want to show that that is in fact a valid equation. How are we going to do this? Now, in the end, we're going to assume that it is correct. And then we're going to check our assumption. And if our assumption is correct, then the equation must be correct as well. So here's how we're going to do that. Here's how we're going to use this, assuming it to be correct, and then checking the assumption. Problem, always phrased in the form of a question: is the thin lens equation valid for a particular thin lens? Why do we say a particular converging lens? Well, because the reality is we're testing one lens each. Just because you find that your lens follows this equation doesn't necessarily mean that every lens follows this equation. There will be three variables. One of them will be a manipulated variable. You'll see pretty clearly as you go through the procedure what that is if you're aware of it, if you're paying attention to it. Responding variable, same deal, there's one of them. Control variables, there's a bunch of them. But there's going to be one or two that are really, really important as always. Those are the ones that you really want to make sure that you have. If you're missing those ones, then you can't get marks for them. What do we need for materials? Well, it's pretty simple for materials, actually. We've got two things. Now, those two things consist of several components, but because the optics bench apparatus comes as a kit, including a candle holder, a meter stick, a lens holder, a card, and so on. We're just going to group it all together under optics bench apparatus. The one thing that doesn't come with the apparatus is the lens. Now, you're going to find most likely that the lens is inside your apparatus, but it didn't come that way. It's just there because people from another class just put it there when they put it back. You should get one bag of stuff and a meter stick, and it should all be there. If you're missing something, let me know. What's the procedure going to look like? Well, the first thing you got to do is find the focal length of the lens. Now, you're going to find the focal length of the lens by putting the lens on a meter stick, like I showed you the other day, putting the screen on the meter stick, like I showed you the other day, and pointing the lens at a far-off object. You want to do it somewhere where it's fairly dark. So in this room, for instance, we could flip off the lights and then peek through the closed blinds. Look at something far off so that the rays of light are pretty much parallel to the principal axis. You will find an image on the screen where the focal length is. The rays will converge at that point. So literally, just aim the lens at this object and then move the card around until you see a good sharp image. That will appear somewhere between 10 centimeters and 20 centimeters from the lens. So wherever the lens is, the card will have to be somewhere between 10 and 20 centimeters away from it in order to get that sharp focused image. That's your focal length. You need to record that on your data right here. Let's say that I found my focal length to be 12 centimeters, then that's what I'd write down, 12 centimeters. Again, you're going to find most likely that it's somewhere between 10 and 20. Now, you're going to go to actually do your experiment. Your experiment is going to be set up like this with the card, the lens, and a candle. The candle is going to be your object. In a dark room, you're going to light the candle, and you're going to place the candle right here at the end of the meter stick. You're going to leave it there. Do not move the candle. Put the candle at the end of the meter stick and leave it there. Got it? The card, you're not paying any attention to the card or the screen right now. The next thing you're going to do is place the lens at a distance away from the candle. So if this is the fixed position of the candle, you're going to place the lens a certain distance away from it such that DO, that distance right here, is bigger than your focal length. If your focal length is 12, don't even make it 13 or 14. Make it 18, 17, 18. Make it significantly bigger than the focal length. The reason we want to do that is because if we put the candle and the lens less than 12 centimeters apart, then we're going to get an image that's virtual. And we're not going to be able to measure the properties of that image. Okay, we want a real image formed so that we can measure the properties of that image. So make sure that DO is bigger than F, and by a fair little bit, by several centimeters. Okay, so pick a spot. Right? If your focal length is 12, pick a spot, 16, let's say. Right? Distance from my screen, sorry, from my candle to my lens is 16 centimeters. Then what you do is take the card and move the card back and forth until you see a focused image on the card. Don't move the lens now. The lens is in a fixed position. Okay, you made your focal length 12 centimeters. You made your object distance, let's say 16 centimeters. Now you got to move the card back and forth until you see that focused image. Wherever you find the focused image, that becomes your image distance. Then you repeat it. You repeat it by changing the object distance. Don't move the lens back and forth. Just move the lens another 3 or 4 centimeters down the meter stick. Measure the new object distance, and then move the card back and forth until you see a good, clear, sharp, focused image on the card. What does a good, sharp, focused image look like? Well, you're always going to see light going through the lens. Just like when I take my glasses off and look at you, I'm going to see light on my retina. It's just not going to be a sharp, focused image on my retina. There's always going to be light going through. This is not an image despite the fact that you see light there. That's like me having my glasses off and light shining on my retina. This is an image. If you look closely at this, this is a picture of an upside down candle. It's a clear image of the object. Hey, that's what you want to see, something like that, not something like this. So pick an object distance, whatever it is, keep it there. And then move your card back and forth until you see this. Maybe it's bigger, maybe it's smaller, depending upon your object distance. Then change this distance right here, your object distance. My recommendation would be to do it not by changing the position of the candle, but do it by changing the position of the lens. Just slide the lens down a couple centimeters. New object distance, and then move the card back and forth until you see a good, clear, sharp, focused image that looks something like this. Record your values. Whatever you get for object distance and whatever you get for image distance, make sure you have 10 trials. 10 object distances, 10 image distances. You're going to change the object distance and you're going to get 10 resulting image distances. Got that? You are going to change the object distance 10 times and we'll see how the image distance responds to you changing the object distance all 10 times. Then you're going to create a new table, which is the inverse of the object distance and the inverse of the image distance. So it's going to be 1 over DO and it's going to be 1 over DI. The units, by the way, 1 over centimeters. An easier way to write that is sometimes just centimeters to the minus 1. And then you're going to plot a graph. And what's kind of neat about this graph is how it's different than any of the graphs that you've seen before. It will be a straight line, but it will be a straight line sloping downwards this time. For the first time, we're doing an activity where it's not sloping upwards. It's sloping downwards. We know how to deal with this, though. Right? We know how to deal with this. Every time you see a straight line graph, you need to come up with an equation for it. And the equation for this graph, as any other straight line graph, would be y equals mx plus b. My y-axis is 1 over di. M is my slope. X is 1 over do. And for the first time, you cannot scratch off b. There is clearly a y-intercept here. It clearly does not go through the origin. So there is a b, there is a y-intercept. Now what you want to do is get an equation from your data sheet, same as we've always been doing. Let's say 1 over f is equal to 1 over do plus 1 over di. Remember I said you're making an assumption that this equation is correct? Here's where the assumption is being made. But we're going to check that assumption. If the assumption is correct, then the equation must be correct. Let's rearrange this. Take the same form. 1 over di is equal to negative 1 over do. If we take that over by subtracting, plus 1 over f. Start crossing things off. 1 over di disappears. 1 over do disappears. What are we left with? Slope is equal to what? Negative what? What is it? Negative 1. The slope is negative 1. You will have a slope of negative 1. You will have a slope of -1. You will have a slope of -1. The slope isn't going to do anything for me because everybody's going to get a slope of -1, or at least really close to it. Theoretically, it should be -1. What we care about this time is the y-intercept. The y-intercept will correspond to 1 over f, right? 1 over dO plus b, 1 over dO plus 1 over f. This is what we care about. The focal length will therefore be 1 over b, 1 over whatever the y-intercept. And Google Sheets will tell you what the y-intercept is, right? It's the second number in the equation. The first number is the slope, the second number is the y-intercept. Calculate that slope. You've already measured the slope. Now you've calculated it, compare the two. If the two are equal, then your assumption was correct and this equation is valid. How do you know if they're close enough to being the same? Because the reality is they're not going to be exactly the same, right? Do a percent difference. Your percent difference is actual minus theoretical over theoretical times 100. This is what it should have been. This is what you measured it to be in the first place. Okay, this is what you determined it to be at the end of it from your graph. So this is the value that you got from your y equals mx plus b graph. If that number is less than 10%, then it's pretty safe to say that the equation is valid. If it's more than 10%, you say that it's not valid. And then, of course, you're coming up with two or three good sources of error, plus your suggestions for improvement. What do you got to hand in for this? Well, it's on Google Classroom already, but basically it boils down to your problem, then your variables. I've already given you the problem. Variables, data, analysis, conclusion, and sources of error.